Hello everyone, today we are going to discuss a very important feature of Java 21, that is virtual threads. I think this is the one feature which will make everyone update to Java 21 as and when it is a general availability on 19th of September uh, this year. So, but today I'm not going to discuss much about this feature, but I'm going to show you the real advantage and the real use cases of this feature and I want to burst some myths, and I also want to bring out some of the truths which people might be having in their mind. And let's get started. So this is the Java 21 homepage for OpenJDK, and here we have the virtual threads feature. In the virtual threads feature, mostly people have, as per my communication with the interaction in my posts in LinkedIn and other places, what I hear from people is that virtual threads are something which are magical, which can really increase the throughput of your program, and it can also make it very easy to code, and it can make everything fast. But that is actually a half truth. It can make your program work faster in a multi-threaded and concurrent paradigm. But the thing it can do is can make it easy for us to uh, code multi-threaded programming, which involves I/O operations and which needs to block the thread. And without we also have this threads as very lightweight because they are like M to N mapping of between virtual threads to platform threads. So it is not a magic bullet which can fasten your application, but that's what we are going to see today. So in our today's code demo, we are going to compare this virtual thread with platform threads in different settings, and also we are going to compare these scenarios, these comparisons between the two, and with a use case where it does not involve any blocking and a use case where it needs blocking. So total of we have 8 cases, 4 cases with virtual threads against virtual threads against platform threads with single thread with the cached pool with a fixed pool of 10, and a use case where we have blocking for 10 milliseconds in each task, and we are doing the same for virtual threads and fixed thread single and fixed pool of 10 and one cached pool. So let's see this in action. So in we can read through this feature of virtual threads a lot. There are a lot of information in this, and this is very vast, and it also gives the understanding of virtual threads and also the previous platform threads. What is the trade-off and why we have come up with this feature? So one of the few of the important keywords which we need to understand during learning this new feature is that it needs that third part request style. So for each request or for each task, we want to dedicate a thread. How it is more easier to do now in virtual threads and how earlier it was being done, and which gave rise to reactive programming and other styles of programming, and how can we scale. So there is a very good example given here for the throughput. So throughput, how can we maintain, what does it take to increase the throughput? So this is the particular example which you can read through, where it compares like what it takes to increase the throughput of a system and increasing scalability with asynchronous style. So when people move towards asynchronous style of coding or reactive coding, reactive frameworks, so it also has pros and cons. So those pros are kept and cons are removed in case of virtual threads. That is what I wanted to convey today. And it so you can please read through it, and let's before going to the code, I would like to make everyone aware that I maintain a code repository called Java 21 and a Java 20. Java 20 is basically a Java 20 based code repo, and it has a support of the Gradle plugin. With Gradle plugin, latest Gradle plugin is not yet ready for Java 21 at this time. So in order to take advantage of Gradle and like for a build system to be there for a complicated with the classes which needs other classes. So this is the Java repo, and in this I am maintaining virtual threads because virtual thread was a preview feature in Java 20, so we can also run that here. So in this folder, in this module, we have all the Java 21 related Java 20 virtual threads. So in this, we have two programs. One is my favorite Java sites program, which showcases the strength of virtual threads. But today we are going to compare this and compare the performance of virtual threads among others. So we are using the password util.java. So in this, let me take you through this program. This program is already there in the Git repo. So let's dive into the code. So this is our password util class. What it is using is mostly a cyclic barrier. I'm also showcasing here, so I will not concentrate more on the cyclic barrier here. 1 minute, let me. Yeah, so I will not focus much on the cyclic barrier part. Here, I'm just trying to show that the design patterns we used to use with previous platform threads are also relevant in the case of virtual threads. And that's why I'm using a cyclic barrier to make it more interesting. Apart from that, we are using executors of different types. And so what does it program do is that it will, we are making the thread count to be generated as 1,000, and each thread generates uh, three characters, and every a group of two threads for a cyclic barrier, it will create one extra special character. So that is what it will do. So, so here it will, you'll have this parties of two means it will create threads. For every two threads, it will inject one special character in the password. So total, it will for 100,000, it will be 3,500. And similarly, that's why we are showcasing it with 1,000 threads to show how much. And we are the comparison factor here is the total time taken. So here we are going to ge- generate 1,000 threads, and the one is the cyclic barrier to inject the special threads. But we are going to switch it off the cyclic barrier for the single thread scenario for a platform thread because we need a party of two. So this is the main method. You can see that I have already coded for brevity purposes one executor for new virtual thread per task executor. What does this executor do? Is that it creates a virtual thread factory, and it will create, we will be spawning 1,000 virtual threads for each task. So we'll not pool them. We'll just keep on creating 1,000 virtual threads. And the second is the virtual thread, which will create. I am creating this executor in the try block because it is auto closable. So it will close itself. I think it was included. Let me see. Okay, so it will close itself at the when the try block ends. Create a executor service which with cached thread pool and platform threads, and this will be a new fixed thread pool of 10, and this will be a single thread. We'll compare the performance of all this, and we are going to spawn and we are going to generate data. So each thread will be generating a random character, a single small letter character, a single digit, a random digit, a random capital case character. And every it will cyclic barrier will wait for two threads, and then what this cyclic barrier will do is it will inject a special character, that is a random special character generated, which is one of these seven, eight. So this is the program, and let's see this in action. So I will just go to the top. So first of all, I will run the virtual thread flavor of this program. In this, it will spawn 1,000 virtual threads and create a password of 3,500 3,500 characters. So let's run this. It's finished. As you can see, so this is the use case where you can see that it is taking 0 seconds and 34 milliseconds. 34 milliseconds, and this is the password. This is the password created of 3500 length. So in this, the basic thing is that we are not blocking the thread. It is just generating and completing, generating and completing. Also, every thread is generating three, and then waiting for another one to come, and then generating like randomly generated special character. This is how it is doing. So this is a non-blocking case where we are seeing that it is 34 millisecond. So just keep a note that it is taking 34 millisecond for virtual threads. Now I will comment this and then show you the case of cached thread pool. So this is the platform thread pool example. Here the benefit here is that we are caching the already created threads. So the time taken for spawning new threads is the it makes the difference. So we can see that it will create a unbounded thread pool, but as and when we want to reuse the previously created one, they will be also available. It should not be destroyed. So now I created thread pool with a keep lifetime of 60 seconds. So obviously our program is running less than 1 second, and therefore it will be pooled. So you can see this is keep alive for keep alive time when the number of threads is greater than the score. This is the maximum time this excess idle thread will wait for the new task before terminating. So we are taking advantage of the pooling. So let's run this. So this is also over. Now you can see the it is taking lesser than the previous one. Let me almost equal or lesser than the previous one. So it is better than the virtual thread. So isn't it a surprise that it is the platform thread is worth because it is not blocking, so it is almost the same. It is doing the same work without blocking, and we are having many platform threads available for this task. So it is achieving the similar kind of time. And let's try it with fixed thread pool. This fixed thread pool will create a thread pool of 10, and it will keep it alive. So this 10 threads creates a thread pool that reuses the fixed number of threads operating off a shared unbounded queue. So almost n threads, 10 threads will be active processing the task if additional tasks are submitted when all tasks are active. So always we'll have 10. So let's run this. So this took better almost half of what the cache thread pool was taking. Isn't it a surprise now that we are only giving it 10 threads in a fixed platform thread pool, and then also it is taking almost half, but it is performing better than virtual threads. So you can see that virtual threads are not faster performing threads. It is helping us to create dedicate one virtual thread per task. So and it is then internally the JDK is Java virtual machine is then seeing or scheduling these virtual threads over the platform threads whichever is available. It is trying to manage those virtual threads, let's say 1,000 virtual threads over the some few number of platform threads. And when we are giving it 10 platform threads in a fixed pool, then it is using all these 10, and as soon as it is taking all the work of taking the work of other 10 as and when it is completing. Now the interesting part comes that I am using. So you might be saying, okay, if 10 is the one, if 10 is taking 17, so let's see how much a executor with only one thread will take. So I'm running it. Yeah, before this, let me also explain why it will take it is taking it is actually hanging. It is because so this is the important thing here that it is a single thread executor means it will create one thread and it will use that thread for the entirety of this program for the entire cycle. But we have a cyclic barrier which needs the party of two threads to perform a something or something special. So this is so a single thread will never have another coming to it. So it will hang at this point. It will await for eternity and it will time out. So let's comment this part for this thread only. So that much we can do, right? So we can, because this concept will not work for a barrier. Or I can do one thing. I can just make it one. This is something unscripted. So let me make it one party of one. So for every, it will keep on, the thread will keep on flowing and there will be nothing happening. So let me, yeah, running it. Yeah, run. So you can see that it generated a large number, more than 3500, because it is generating 4 characters per thread. So 1000 threads created, 10 thread, basically one thread only doing 1000 tasks. So each task generating 4 characters and now, and therefore it generated more number of characters, random characters in 14 seconds. So it is taking lesser than the time taken by a fixed thread pool of 10 threads. 10 platform threads are executing in more time than one single thread. That is amazing to see in this program, that how just by increasing the number of threads, it is not increasing the throughput. Throughput as in, like, in a particular given time, it is giving more results. If I say 1 second, if I run this program for 1 second, I will get more number of characters, random characters from one thread than 10 threads. So the trade-off of creating new thread platform threads and then managing them and switching between all tasks from one thread to another task, all that is increasing the time by few milliseconds in the case of this thread pool. Now these are the 4 cases for a non-blocking case where there's nothing blocking the thread. They are just they're generating random characters one by one, adding it to a concurrent list. So, and that is creating the passwords. Now I will just do these are the 4 cases. Now I will do another 4 cases with a blocking scenario. So you in this scenario, in these 4 scenarios, what we could find out is that number of, first of all, the virtual thread is performing well. It is performing within almost like suppose 50 30 or 40 milliseconds, and single thread is the least is 14 milliseconds, and the maximum virtual thread it is 35 milliseconds, 35 40 milliseconds. It's a magnitude double or almost triple, but it is not that bad. It is not taking like 1 second or 2 seconds, or in a magnitude of 10 times more time. So we can see that that is what we saw, that virtual thread is not the fastest here. It is basically the slowest. So if I show you, let me close these classes. So this is the without IO. So you can see in without IO, you have single performing well. It is the data, similar data which I am showing you here. So single platform thread took 15 millisecond, fixed pool with 10 platform threads taking 19 milliseconds, and it is more. Single is less, 10 is more, and cached thread pool of platform threads took 33. So it is even more because it is maybe because of to generate 1000 tasks running parallelly, it is creating more and more number of platform threads. Virtual threads, the JVM is managing 1000 virtual threads spawned over a obviously lesser number of platform threads. Maybe that's the reason it is more, because there are 1000 virtual threads. So JVM took the liberty and created behind the scenes more number of platform threads. So it is 42. So this is almost double. So single is a little better than fixed. Cached is better than virtual, but virtual is the performance worst performance. Now we will do the same test cases over a blocking scenario. So in a blocking scenario, what I will do is I will start with the single. I will I have created a block here. After creating this random letters. I'm mimicking a IO operation of 10 milliseconds. Actually, the in the original GitHub code it is almost 100, but here I'm doing it for the sake of for demo to show the impact very soon enough. I'm making it 10 millisecond. So I'm just stopping the thread from doing anything for 10 milliseconds. And since this is a single thread scenario, so I've already made it one for it. So let's run it and see what happens. So it's still running, still running, still running. It is a blocking scenario. So every thread will at most stop for 10 milliseconds. Even though the work is over, it is stopping. It is basically waiting for some action. So I'm mimicking the IO. Let's suppose it may be a database operation. It may be a REST call to some API, some microservices. So you can see it generated 4,000 characters, random characters for a password in 15 seconds. So if you remember from the previous one, it was taking 16 milliseconds. Now it is taking 15 seconds and 579 milliseconds, almost 15.5, 15 and a half seconds. And this is 16 milliseconds. So you can see the magnitude is almost 1000, much, much more for a blocking scenario. So in a blocking scenario, one single thread working hard and every time it has to stop for 10 milliseconds. And therefore, the 10 milliseconds into 1000 is obviously 10 seconds. So 10 seconds out of this 15 seconds is a waiting time, and others are all are 5 seconds, and other 5.5 seconds are the one which is working. Now let's make it more interesting. We'll try the fixed thread pool scenario with the 10, and I just wanted to make it to again 2 so that because the 2 because of the fact that this will work with the two parties. So let's run it. So it took 1 second and 1.5 second actually. So 1.5 seconds. That was 15 seconds. This is 1 second because there are, it will obviously, you can see that it is 15 seconds, it is 1.5 because the magnitude of 10 reduced because there are 10 threads. So it really helped to reduce the time by 10 times. So 1.15 to 1.5. So this is the magic of more threads, but obviously for a high performance and high throughput application, we can't keep on increase. When you read the JEP page, you'll find you will obviously it's a logical thing that we cannot keep on increasing the number of threads. I cannot make this thread. I cannot tune this thread to 10 and like maybe in the daytime 100 and then maybe in the weekends 10,000. There is a capacity for the operating system for the memory to accommodate the number of threads, and beyond this thing it will not work. It will just cap itself. So now you can see this is the thing. So it is reducing now in a blocking scenario. In the non-blocking scenario we had the single thread was victorious. Now in the blocking scenario we can see it tweaking. Now the fixed thread is better. Now let's see what happens with a new cached thread pool. So you can see it is taking 10 times lesser. Now it was 1 second, 1.5 second, it is now zero point 0.1 second. So it is reduced to almost 15 times lesser than that. So it is performing much, much better in a blocking scenario. So now comment it and let's see, will virtual thread help us in this scenario or not? So just remember that it is 99 millisecond in the case of cache thread pool. So cache thread pool will keep on creating thread pools and keeping the created threads cached. So we are running it. So what we see is half of 99 millisecond. So now we are almost getting the same performance for a blocking scenario and a non-blocking scenario. For a blocking scenario, we are getting 56 milliseconds. That's half of the cache thread pool. And for a non-blocking scenario also, we were getting something like 40 milliseconds. So the virtual thread is giving a much better 15 seconds for a single thread, 1.5 seconds for fixed pool of 10, and a cache thread pool giving 100 milliseconds. This is giving 50 milliseconds. So you can see virtual thread is, and guys, did you see that for this entire demo, I had just, what did I change? I just changed the executor. I just switched the executor from one to another. So did the code change? Did the code, which is the application logic, change where I am submitting the task? No, I did not have to change anything in the code. I did not have to tweak anything in the code apart from the cyclic barrier, because that is how I have designed the this use case. But I didn't have to change anything. I just keep on switching from one executor to another, another to the another, and that's how I have shown you. So you can see that virtual thread. So in case you have a application code which is working on a fixed thread pool or a single thread executor or a cache thread pool, you can just switch that executor to new virtual thread per task executor and see the change immediately without changing the application code much. So unless you are spawning subtasks from these threads and then creating platform threads. So if you're not doing that, then you can see and you can find. So now to summarize this test cases, these four test cases which I ran. So I'm going to show you. So this is with IO operation. The same thing without IO operation, single. It was almost comparable. You can see, obviously the single is almost half, one third of the virtual, but it is the magnet. If you see the y-axis, it is all linear, 10, 20, 30, 40, and it is in within the limits. Now if you compare this with a blocking scenario of an IO operation mimicking with 10 millisecond per thread, single is taking, I don't know what to say, 6.5 million milliseconds. And then this comes, the fixed one is, this is another data which I did before. This is 600,000. It's almost 10 times less, obviously, with logically divide by 10. And then cached is just 225 because it is having unbounded. It is an unbounded pool. It will keep on creating, but cache the threads for further use. And virtual is almost 50% less than that. So you can see changes here between the, you can contrast between this and this. Now you can, I don't have to spell out, or I don't have to suggest anything here. You can see that virtual threads are working without any change, major change. Only the executor is changing. It is taking care of your spawning of virtual threads, and it is making drastic changes in your application performance. Um, thank you everyone. I hope you might have gained some insights into this. Thank you for joining the call today.